You definitely have a lot of devices lying around, your smartphone, tablet, or a computer. Your smartphone has a virtual assistant. Your computer has predictive text. These kind of smart devices are all around us. So it's essential to know how these things work. Hi, my name is Aditya and I welcome you to Deep Learning and AI. In this class, we will be learning how to build our very own neural network without any math or calculus background. We will be using TensorFlow, which does all that for you. With a neural network, you can build cool things like an image classifier, like the one used in Google Lens, or write poems with it, or do any other task you throw at it. For taking this lesson, you will be needing a basic Python background, and a basic machine learning background won't hurt. But don't worry, I'll explain most of it as we go. We will be using Python and TensorFlow. TensorFlow being a library which has lots of useful machine learning and deep learning functions which we can then use. We will be coding in Google Colab, a free service where we can execute machine learning code while not worrying about computational speed or time. The content of this class will be defining a neural network, building a basic neural network model, building an image classifier for cats and dogs. Then we will be using the famous fashion MNIST dataset to build a clothing item classifier. And we'll do this all in less than 100 lines of code. I promise you, in no time, you will be making neat stuff with neural networks, and I'll see you in the next lesson. We are used to creating applications by breaking down requirements into composable problems that we can then code. If we are writing a game, we give it rules like if the player touches a power-up, he grows stronger, or if he is hit by a fireball, he loses a life. So rules and data go in and answers pop out. In machine learning, we put answers and data in, then we get the rules. We give bunch of examples to our programs and a desired answer and let the computer figure out the rules. Consider this example I saw in a video. If I am doing activity recognition and I have different speeds provided to me as data, I can define walking with a particular speed like this. And if I also have to do running, I can do this like this. And I can do biking as well. But then I have to do golf for any other sport. Then just with speed data I can't do it, so my program becomes broken. So what we can do is we can express this problem by providing lots and lots of data and then labeling them by saying, hey, this data is walking, this is running, and this is biking, and this is golfing. So by providing this data to our program, we let the machine infer what are the rules. Let's take an example. I like you to solve this equation. What do you think is the relationship between x and y? Take a minute. I hope you got this answer. The relationship is y is equal to 2 times x. Congratulations, you did basics of machine learning in your head. A machine learning algorithm figures out the patterns in the data and provides distinctiveness in each. We will be learning how to build a basic neural network first, and then by the end of this class we will be building a computer vision model which can identify different things. So now we will go on and build our first neural network and see how everything works. Before we start, I would like to familiarize you with parts and aspects of a neural network. A neural network is made up of layers: input layer, hidden layer, and output layer. The input layer is where input is given to the network. If we are making an image classifier, we will input the pixel values of the images. The hidden layer is where all the heavy hitting happens. Each hidden layer has a weight and bias associated with it. The value of weight and bias helps the neural network to learn different things. How this learning takes place is out of the scope of this class, and it requires a mathematical and calculus background. Luckily, all this math is implemented for us in the form of TensorFlow functions, making it extremely easy to code. Having the background will certainly help you build a better neural network, but it is not required for beginners. To get a basic understanding of neural network, I recommend you to go and check out playgrounds.tensorflow.org. This is an excellent tool to understand how things work in a neural network. This is a classification problem where the background will try to map the respective colored dots. Try out different combinations and test how it affects learning. The learning rate is how fast or slow your neural network will learn. To have a value very high will cause problems reaching a reasonable solution, and having a value too low will increase the learning speed. Activation. Activation is applied to each layer in a neural network except the input layer. The activation basically shifts the value range of the particular neuron. For example, if we choose ReLU shifts the value of the negative numbers to 0 and will keep the positive numbers. And if we change it to sigmoid will transfer all the values to a range between 0 and 1. So it can transfer values between 0 and 1. We use them in binary classification. Regularization helps us to overcome overfitting and underfitting, which we will cover in a later lesson. So I recommend you guys to check out how different classifications work and test out different combinations. Google Colab is a free cloud service where you can improve your Python programming skills and develop deep learning applications using popular libraries such as TensorFlow and Keras. Unlike coding on your local machine and downloading a bunch of libraries, all these libraries will be pre-installed, so saving up lots of space on a local machine. As machine learning or deep learning is a computationally heavy task, we can use the free GPU provided to train our model faster. The only requirement is an internet connection and a Google account. So when you open up Colab, you will be greeted with a welcome page. You can read it and learn more about it. Still, we will skip it and then click on New Notebook. This notebook will be saved on your Google Drive. You can save it on your local machine by going here and saving it as a Python notebook or as a Python file. To change it to dark mode, go to Tool Settings, and under Settings you can find Themes where you can change it to dark mode and then hit Save. So to execute code, we go to the cell, write out code, then press Shift Enter or hit this play button. This will execute our code and then the output will be displayed below the cell. I want to share more information about Colab, which I will do in a later lesson. So this was a basic introduction to Google Colab, which will be sufficient for our use case. To get in-depth knowledge about it, go to TensorFlow's YouTube page to find more information. So before we start, I would like you all to recall the problem we discussed in the previous classes. That is, giving a relation between x and y. The relation we found out was y is 2 times the value of x. This is the basic of a machine learning program. I will also like you to recall that in machine learning we put data and answers in and get the rules as an output. So we are going to apply these concepts here. We are going to use TensorFlow and Python for programming. You will find that a lot of information is coming at you at once. So don't be intimidated by it. All of this is extremely simple to understand. First line of code is to define our model. Our model is the neural network. So the neural network can be defined with the sequential function. A neural network works in a sequence, that is, we provide an input, it goes to the input layer, the hidden layer, and then the output layer. To define the layer, we use the dense function. To define the number of neurons inside the layer, we give units, in this case 1. The input shape is the shape of the input. In our case, we are only giving it a single digit. The next line of code requires a little bit of math understanding. Luckily, all the complicated calculus and math is computed by Keras in the background. The only functions that you need to know are optimizers and loss functions. Optimizers optimizes the model, whereas the loss function tells the optimizer how well it is doing. For example, when we execute our model, it does not know the relationship between x and y, so it makes a guess. It guesses y is equal to 20 times x, which is wrong. So the loss function takes the answer that it guessed and checks it with the actual answer and tells the optimizer, hey, this is how much you were off. So the optimizer then makes a educated guess again, and the loss function does it again. And with each of this iteration, the neural network keeps on learning better and better answers. The next line of code is just providing input. If you are familiar with Python, then you will know that we are defining a list. If you're not familiar, I will recommend you to go and check out my previous class. That is Python Easy and Fast. We are using NumPy to define an array. NumPy is also an inbuilt library which helps defining lists extremely easily. Dtypes is just the data type which we are providing. X is the input that we are giving to the neural network, and Y are the answers that we expect. The fit function will fit, or in other words, will help our model to learn. So we provide them with the input, which is X, and the answer we expect, that is Y. Epochs is basically just the process that I described earlier, that is optimizer making a guess, the loss function checking the guess, and optimizer making the guess again. So as you can see, after 20 epochs, we have an extremely low error. So now we will use the predict method to predict the answer of 14. The relation that we found out was 2 times x, so the answer should be 28. But you will see the answer it gives us is 27.9, which is extremely close to 28 but not 28. This happens because machine learning or deep learning deals with probabilities. So when it makes an educated guess, it is not 100% sure that the answer that it provides is the actual answer. So it provides a statistically viable answer that is extremely close to actual answer but not 100% accurate. This will be true for many other programming aspects in machine learning. So now that you have written your first neural network, I would like you all to code this on your own and play with different relations. And I will see you in the next. Overfitting and underfitting. This is a very simple and important concept to learn. It will help you to build better models for your application. In the first graph, the orange line going through the data is a good solution and it fits the data well. And the blue line is the line we get out of our network. As you can see, it doesn't do very well in predicting the value of y. For example, let's take this new point. So just by looking at it, we can say the value of y will be somewhere around this neighborhood. But our model predicts the value which is way off. So we can say the model has underfit the data, as it does not predict the training data well and does not do good on new data either. The next graph is very close to the good solution and can predict the value y with good accuracy, even when new points are given. This is what we are looking for when we are creating a model. The third graph is where the model fits the given data or training data too well. At first it might not seem a problem, but as soon as you give it new unseen data, it falls apart. As you can see, the model captures the data points extremely well. It even gets the peaks and troughs. This causes the model not to generalize well with unseen data. For example, let's take this point here. So it is safe to say the value of y for the particular x will be somewhere around this region, but our model predicts the value which is way off. So we can call that this model has overfit the data. So as a summary, overfit predictors or models is too complex and it fits the patterns that will never occur. It has better accuracy on training data and lower accuracy on unseen data. Underfit predictors is very simple and does not capture the pattern in the data and does not do well overall. When we create a model, we need to strike a balance between both. We need to fit the training data well while maintaining a good solution for predicting new values. So this was underfitting and overfitting. To get rid of them, we can use techniques. A few of these techniques are: to reduce underfitting, we can increase the model complexity. that is add more layers or add few neurons to the model. We can also reduce underfitting by increasing the number of epochs, that is the number of cycles we go through. To reduce overfitting, we can use different techniques which are increasing the number of training data, that is providing the model with a larger number of training data. Other techniques are to reduce model complexity, that is to reduce the number of layers or reduce the number of neurons. Early stopping is a technique where we stop the training of the data when we notice the loss is trying to increase. Regularization is a technique which we add to the loss function so that it does not overfit the data. So this was underfitting and overfitting, and we will see more about this in our programming lesson. Before we make our first image classifier, we need to understand our data. It is a very important step while building any different type of models in machine learning or deep learning. I have provided the link for our dataset so you can download it for yourself and see the images. The dataset has two subfolders, training and test data, and in each of them there is a folder with cats and dog images. These are colored images. A colored image has three channels, that is R, G and B, that is red, blue and green channels, and each pixel in these channels has a value range between 0 to 255, 0 being dark and 255 being a bright pixel. When we convert our images to an array, we get a dimensional array with each element being a pixel value. This is our input to our neural network model. As these value ranges between 0 to 255, it becomes very difficult for our model to learn as the value range is extremely high. So we normalize this and convert this into a range between 0 to 1. We can do this by dividing every single element by 255. So the range will be between 0 and 1. This is an overview of our data. We will learn more about how we can feed this information to our neural network so it learns to identify between cats and dogs. When you learn to build your own models, most of the dataset you will use will not be divided or labeled for you. You'll have to do it for yourself. So in this lesson, we'll take a look at some APIs that are available to make that easier for you, in particular the image data generator in TensorFlow. One feature of the image data generator is that you can point it at a folder and then the subfolder of that will automatically generate labels for you. The image generator class is available in keras.preprocessing.image. You can then call an image generator like this. I'm going to pass rescale to it to normalize the data as we discussed in the previous lesson. You can then call the flow function from the directory method on it to get it to load images from the directory and its subdirectories. It's a common mistake that people point the generator to the subfolder. It will fail in that circumstance. You should always point it to the directory that contains the subfolders. The names of subfolders will be the labels for your images that are contained within them. So make sure that the directories are pointing to the correct one. Now images might come in all shapes and sizes. The input data all has to be the same size, so the image will need to be resized to make them consistent. The nice thing about this is we can code the images to be resized without actually changing them, and these resizing is done as they are loaded, so you don't need to pre-process thousands of images on your file system. The advantage of doing this at runtime like this is that you can then experiment with different sizes without impacting your source data. The images will be loaded for you in training and validation. These data will be divided into batches. It is a more efficient way of doing things rather than going through the images one by one. Now there's a whole science to calculating batch sizes that's beyond the scope of this class, but you can experiment with different batch sizes to see the impact on the performance by changing this parameter. Finally, there is the class mode. Now this is a binary classifier. That is, it picks between two different things, cats and dogs. So we specify that here. Other option in particular for more than two things will be explored later. The validation generator should be exactly the same, except of course it points at a different directory, the one containing the subdirectories containing the test images or the validation images. This is what we will be using to feed our images to our network. In this lesson, we will be building an image classifier that can distinguish between a cat and a dog. This won't be our final model. We will build a better model in the later lessons. I'll go through the code and explain it. The first few blocks are just importing the libraries. The Google Drive libraries are required for getting our dataset. To use the dataset, upload a zip file to your Google Drive, and after uploading, use the same account to start a new Colab notebook. After starting the notebook, go to runtime and then change runtime settings, where you can find an option for hardware acceleration. Under that option, select GPU and then press save. Using a GPU vastly increases your computational speed. The third block will ask you to authenticate yourself and will provide you with a link. Press that link and choose your account. With the dataset, after accepting the permissions, you will be given a key. Copy and paste that key in the box below. This will successfully mount your drive. I have seen many different ways of doing this, but I have found this method to work the best. If you have any other suggestion, please feel free to share it with the class. The next block is for getting a dataset from our drive. Our file name is dataset, so we write dataset here. If you are using any other file, use its name. Next, we unzip the file to the folder and its subfolders. The next block is the image data generator function, which I talked about in the previous class. As you can see, we have 8000 images in our training data and 2000 in our validation data. Next, we create our model. The flatten function reshapes our 3D array into vector that is only 1D. So we can use it as an input. In the last program, we did not use this flatten function. Why do you think that is? The next line is creating our hidden layer. As it is a more complex problem, we will be needing more neurons and more layers. I have just used 2 layers here. I recommend you to try it with more layers and more neurons and observe the results. We compile our model this time and we use Adam Optimizer, which is a powerful optimizer. I recommend you to go and check out TensorFlow documentation for details about it. When we fit our model, we add one more parameter, that is validation data. This will fit the current model with our validation data with respect to the epochs. So when we execute our model, it starts to fit. This takes quite some time to run because of the number of images, but we are using a GPU, so the speed is increased. As you can see, we have a low loss and an accuracy of about 60. If you went through the images in the dataset, you would have noticed many images had wasted negative spaces or spaces where the features weren't present. There is a way we can condense these images down to the essential features that distinguish an image from a cat or a dog. We use convolutions to make that happen. It usually involves having a filter and passing that filter over the images to change the underlying image. The process works a little bit like this. For each pixel, take its value and take a look at the value of its neighbor. If our filter is a 3x3 filter, then we can take a look at the immediate neighbor so that you can have a corresponding 3 by 3 grid. Then, to get the new value of the pixel, we can multiply each neighbor by the corresponding value in its filter. So for example, in this case, our pixel has a value of 192 and the upper left neighbor has the value of 0. The upper left value of the filter is -1. So we can multiply 0 by -1. Then we could do the same for the upper neighbor, its value is 64 and the corresponding filter value is 0. So we multiply those out. Repeat this for each neighbor and each corresponding filter value. And then we have the new pixel with the sum of each of the neighbor values multiplied by the corresponding filter value. That's a convolution. The idea here is that some convolutions will change the image so that the certain features in the image are emphasized. So for example, if we look at this filter, then the vertical lines in these images will pop out. With this filter, the horizontal lines pop out. Now, that's an elementary introduction to what convolutions do. And when combined with pooling, they become really powerful. Pooling is a way to compress an image. A quick and easy way to do this is just to go over the image 4 pixels at a time. Of these 4 pixels, pick the biggest value and keep just that. So for example, you can see it here. My 16 pixels on the left are turned into 4 pixels on the right. By looking at them, convolutions are highlighted while simultaneously quartering the size of the image. If you have trouble understanding them, don't worry. We will see them in action in the next lesson and we will get a better understanding. Now we are going to apply the things we learned in the previous lesson about convolutions and pooling to the dog versus cat classifier. Most of the code stays the same. The model definition changes a bit and we add convolution layer and max pooling layers to our model. The conv2d layer defines a convolution layer. The 64 is the number of filters we are going to use and 3 by 3 is the shape of the filter. The max pool layer will be the next line of code and will halve the image. I apply these few more times to condense the images. The next block will give us a summary of our model. The first conv layer takes our images and reduces it by 4 pixels. This happens because of the convolutional operation I mentioned in the previous lesson. The reduction in size depends upon the filter size. To prevent it, we use padding. Padding will add an extra layer of pixels with the value 0 to the perimeter of your image. So when we perform convolutions, we retain those pixels and we do not lose the 4 pixels like in this case. I'm not applying padding here. If you wish to add it, use this syntax and pass it with the respective conv layer. Now we compile and visualize how conv layers work. We take 3 images and pass it through our conv layer. As you can see, the image reduces in size. From 150, it went down to 34, while maintaining the general shape of a dog or a cat. The bright outlines are in the form of a cat, and this one is of a dog. So now we will execute our model. This will take a few minutes. Now that our model has finished learning, we can see our training and validation accuracy is quite high. This is way better than our previous model, and we did it just by adding a few lines of code. Still, deep learning and machine learning are iterative processes, and to get a really high accuracy on unseen data, the tweaking the model by adding neurons, removing layers, etc. goes a long way. I will like you to add padding and see how it affects the results. In the next lesson, we will classify multiple clothing items using convolutions. In this lesson, we will build a model that can perform multiple classification. We are going to classify different clothing items. We will be using the MNIST fashion dataset for our task. So MNIST is a database and stands for Modified National Institute of Standards and Technology. You would have heard about it because of the popular handwritten dataset. So TensorFlow has an inbuilt function to import this dataset, which makes it easy for us to use. This dataset is also pre-labeled and divided into train and test, so we don't have to apply the image generator function. There are a total of 70,000 images of size 28 by 28 and only have one channel. This dataset has 10 different clothing items, so we need a different activation function in our output layer. Previously, we were using the sigmoid function, which is great for binary classification. Its value ranges from 0 to 1, but now we need to calculate the value of all the different classes, and sigmoid just won't cut it. So we use softmax. It is an activation function that gives probabilities of all the classes, and the value of one unit will be greater than all the other units, and that will be our predicted class. So for example, let's take a new model which has already learned how to classify between a shoe, bag and a cap. So we feed this network with an image of a shoe. So after going through the model, one unit which represents that the image is a shoe will have the highest probability compared to the 3 units. So now we will use this to build a new model to classify different fashion items. The multi-class classification doesn't differ much from binary classification. A few minor changes here and there and we will have a new classifier in no time. As I mentioned in the previous class, we have an inbuilt function for retrieving the dataset. This dataset has a total of 10 different classes or clothing apparel, 0 being a t-shirt, 1 being pants and so on. This is a plot of a sneaker from the dataset. This dataset is also labeled and divided, so the only pre-processing we need to do is to add the channel, that is the one channel it has, and normalize the data from 0 to 255 into 0 to 1. After doing that, we build our model. As these images are only 28 by 28, we do not need to add many convolutional layers or Maxwell layers. The model syntax remains the same, and the only thing changing is in the last layer, where we change the number of units from 1 to 10 because we have 10 classes, and then changing the activation to softmax. As the summary tells us, the image is 13 by 13 in size, and the 64 defines the number of filters we used in the conv layer. We also change the loss function to sparse categorical cross entropy to compute loss for all the classes. We used binary cross entropy in the previous lesson, which won't work because we are dealing with multiple classes here. If you want to know more about the loss function and optimizers, I recommend reading the TensorFlow documentation. This model can be improved slightly, and I leave it up to you for deciding how it can be done. A hint: it involves adding a layer to the model. We got a really good accuracy of about 0.9 on the training set, and now let's check its performance on the test set as well. This line of code will evaluate the test images with the learned model. It can be visualized as the forward pass where the model makes the guess and does not learn. We also got a great accuracy of 0.9. In deep learning, it is often very difficult to approach test set accuracy and can be very time consuming. So for our model, an accuracy of 0.9 is quite good. If you want to improve upon it, go ahead. I have already given you a hint. In the next block, we will test some photos. I downloaded a few images of the internet to test. The first image is just an image from the dataset. It is a pullover t-shirt and it should classify it correctly. The second image is a model wearing a pullover shirt which does not belong to the dataset. It identifies it as well. But as soon as I give it a third image, which is a little off-centered and has lots of roads and walls and a lot of noise in general, it fails. So for example, if you are building an app for classification of these kind of photos, you can expect these photos being used for your model. So when you train your model, these are the kind of photos you need to use. Using centered and clear images will not apply in the real world like in the MNIST dataset. The users will click off-centered, blurry pictures, and your model will have a hard time to detect them. So always have a dataset similar to your application. So I suggest you implement this code by yourself, and in the next lesson we will discuss the class project. For this class project, I will like you to build a multi-class classifier using the MNIST handwritten dataset. It can be imported using the mnist function like this. You can also use any dataset you want. You can find plenty of amazing datasets on Kaggle. Kaggle has a database of thousands of datasets ranging from CSV files to images. If you have watched Silicon Valley on HBO, you can build Jin Yang's seafood application, which basically classifies between a hot dog or not a hot dog. You can go the classic way of just defining hot dog or not a hot dog using binary classification, or you can build a useful app of identifying different foods. Both of these datasets are available on Kaggle, and I have linked to them in this description. Whichever option you choose, download that dataset from Kaggle, import it to your Google Colab like shown in the previous lessons, create your model and share the code of your model with the rest of the class in the form of images, or link your Google Colab to your project. Congratulations on finishing this class. I hope you had fun learning and doing all the programs. A quick summary. In this class, we learned basic components of a neural network, building a basic neural network using TensorFlow, cat versus dog classifier, CNN and max pooling, cat versus dog classifier using CNN and max pooling, multi-class classification, and finally we used the mnist dataset. I hope this helps you to get a hang of deep learning and can use these concepts you learned in your applications. I hope you enjoyed taking my class, and I request you to share this class with your interested friends. And finally, I'd like to thank you for taking my class, and I hope to see you in my next classes.